Hello, welcome and good day. So, for our lecture this week, we're going to talk about electric field. Okay, so this will be a new lesson, then at the same time, an extension to our understanding about electric charges and, of course, the law that governs behind it, which is Coulomb's law. So, our objective is to understand electric fields and then what are the electric field lines, and of course finally to solve problems that involves electric fields. Alright, so electric field is a vector field, okay, wherein something that obeys the Coulomb's law. Okay, so if you're going to illustrate it, so let's say this is your charge. Well, let's say this is there, so there's a circle. All right, so let's say this is positive charge. Okay, so positive charge will have an electric field that looks like this and like this. Okay, something like that, right? So this area outside the circle, so everything that's here outside the circle is what we call the electric field. Okay, so that's the region of space outside, or that is emanating from what we call a point charge. Okay, or a source charge that generates this electric field. Okay, so it's a vector, of course. It signifies both magnitude and direction. So let me clarify that by showing it to you. Okay, so I'm going to increase the number of arrows so you would get what I mean. All right, so there you go. This is just a very rough illustration. Anyway, the arrows are all pointing outward. Okay, so you just keep that in mind there. So there's lots, so I'll not complete it. So we're going to define electric field by looking at the definition here. So we have the properties here. So field lines are actually the space where an electric field is placed. So let's say I'm going to place the electric field on this particular space. Okay, so it means it utilizes I think a polar coordinate system or something like that. Okay, so let's say this is our field space or something. Okay, so it's not an exact technical term, so let's just call it that. So knowing a polar coordinate system, it's a coordinate system where it radiates outward, right? So something like that. Okay, so if it radiates outward and you're going to place an electric field anywhere from on its field, so there will be a electric field. All right, so the field lines will be tangent, so or they will be coinciding. Let's say this is your electric field lines. Okay, then your electric field would be sitting on top of it. If it's on top view, if it's on the side view, it will look something like this. Okay, they will be parallel with one another, actually in tangent, so they will be touching each other. But for you to visualize it, so there, something like that. Okay, so what's the next property? So the greater the line density, the greater the magnitude of the field. So if you're going to look at this illustration, you're going to see that the lines nearer the point charge, okay, has smaller distances between them. So the distance between here and here is smaller compared to the distance between here and here, correct? Or let's take this one. So let's say this one and this one versus this one and this one, right? It's further. So that's what it means by that. So if you're nearer to the center, it means the electric field is greater there. And as you go further away from the center, the electric field gets weaker and weaker, which makes sense, right? So let's say let's create an analogy using a picture. So let's say this is let's say you're standing here and you have two friends that is here standing here, okay, and then the other one is standing here, okay. So of course, knowing how visions work, your friend that is nearer to you will be clearer, right? So let us use that analogy to understand that the nearer you are to the center or to the source of electric force, the greater is the electric field, okay. And of course, as you move further away, so let's say this friend of yours is really far, so the electric field that you will be experiencing is weaker, okay. So the next property is electric field lines always start from positive charge and ends with negative charge. So I'll be explaining this in greater detail later, but basically if you have a positive charge, oh, it's not erasing again, very sad. So let's say if you have a positive charge, so just like what I've drawn here, so electric field is pointing outward, okay. Then if you have a negative charge, so it's pointing inward, okay. As simple as that. Then lastly, field lines never cross. Okay, you're going to see this later on some of our illustrations. All right. So here are the examples. So this will be further explained to you by your teachers, but I just want to show it to you. Okay, so here's the electric field line of a negative charge. Then you have an electric dipole or attracting charges, so one with positive and one with negative charge, okay. So as you can see, it originates from positive going to the negative charge, okay, something like that. And look, they're not crossing, right? Don't mind the black lines yet, okay. We're just going to focus on the blue arrows. All right, next we have for similarly charged particles. So you have two positive charge, and at the same time the two negative charges will act like this as well, but you're going to change the direction of the arrowhead, okay. That's the only difference for negatively charged particles, okay. Then lastly, special case. So this will be very crucial to your understanding as we are going to utilize it more later in this lecture series, okay. So parallel plates, sometimes called as capacitive plates, okay. So this is what we call a uniform electric field, okay. Oops. Oh, it's not deleting. Oh wait, let's, okay, there, see. Anyway, so this is what we call uniform electric field. This, okay? All right. So there's that. Anyway, sorry for that. Okay, so it's uniform because if you're going to compare it to the point charges, going back to those, see, so the line density is greater nearer the charge or near the center of the charge. As you move further away from the center, the density gets smaller and smaller, right? So there. So after knowing those, actually this will be further discussed to you by your physics teachers. So I'm here to start, of course, on the guided practice problems. So for the equation, it's very, very similar in a way because, of course, it stems from that, from what do you call this? Coulomb's law. So not moving up anymore. Bakit kaya? Mabala siya kung ayaw niya. Anyway, going back, so let's have a recall. So Coulomb's law is defined as electric force is multiplied by the Coulomb's constant multiplied by charges 1 and 2 divided by the radius between them. I mean the distance between the charges. Okay, so if you're going to divide this or divide both sides by known as the test charge, okay, so the other one will be a point charge, so the other one will be a test charge. Okay, so this is Q sub test. Okay, so you can just choose either. It will depend on the definition on the problem, so you can just cancel this out, let's say. Okay, so now this will be the definition of electric field. So that will be electric field is equal to F sub E over Q. Okay, test equal to K Q source. So this is now where the electric field originates, okay, divided by the distance to be squared. Okay, so I hope we have an understanding on the matter. So this will be okay, let's say for you to visualize the equation. So let's say we're going to define the electric field of a point charge that has a positive charge. Okay, point charge or a point charge, no, or a source. Okay, then I'm going to place a test charge somewhere here, let's say on this line, on this point. So let's say a positive point charge. Okay, so if you're going to use this definition, all right, so what would happen would be you're going to take the electric field between these two divided by this one. So effectively you're canceling this one out, right? You got that? Leaving you with this this portion, the portion where the electric field originates, or the source, okay, multiplied by the distance where you place your test charge, which is of course somewhere here. You got that? Okay, so after understanding that, we can now proceed on the guided practice problem. So let's take a look at the first problem. So we have here, okay, a small charge is found in a uniform electric field. Oh, this is easy, okay? So take a look and read. Okay, so let's state our given. So first we have test charge of 6 microcoulombs, okay, which is equal to 6 times 10 raised to, I mean, that's milli, right? Sorry, not micro, that's milli. Okay, then we have an electric field of 2.9 newtons per coulomb. Speaking of that, since it has already been showed here, the unit of electric field is newtons per coulomb. Okay, then we don't need any conversion for this one. The required for this problem is the electric force, or just force, okay, if you prefer that. I don't mind naman, pero I prefer this one. It depends on your physics teacher how they want to define the variable. As for the equation, we have, what can we use? So knowing that electric field is electric force divided by this one, so you just need to, okay, so let's call this a test charge. So let's multiply both sides by Q test. Click. So then just place it here. But just assume I multiplied this one, okay? So there. So the final equation would be electric force is equal to Q times the electric field, okay? Or you can place Q test. Again na, Q test na, multiplied by the electric field. There. Then you can now proceed on substituting. So electric force equal to, what's our charge? Actually nandito na siya sa given. So 6 times 10 raised to negative 3 coulombs multiplied by 2.9 newtons per coulomb. Okay, so cancel this. Alright, so what's the answer? So very obvious, right? So the unit for this will be, of course, in newtons. Okay, so you just state it. Okay, so you solve this on your own. Actually, that's the input I'm asking you to do for this guided practice problem. So I'd know na you're practicing it as well. Okay, so that's it for our next problem. We have this. Okay, so we have a cesium 133 is the basis for the fundamental SI quantity time. If its empirical atomic radius is 265 picometers and its van der Waals radius is 344 picometers, how much weaker is the electric field experienced by a single electron from the van der Waals radius compared to its empirical atomic radius? Assume the nucleus as the point charge. Okay, so knowing that this is cesium, we're going to need the atomic number of it. So of course you have to look for that one out, but of course I'm going to provide that one for you on this problem. So see, so first let's determine our so for this one, since we have two equations for electric field, we're going to use the one that uses the Coulomb's law. Alright, so that's kq over r squared. Since we have two distances, right, then we're going to just subtract them. Okay, so first, given we have the charge of cesium, so that's okay, so I'm just going to, or just Q na lang, Q of CE, right? Or CS, I mean CE is cerium. Sorry. So how many atoms are there for cesium. Okay, so you can look for that one up. I'm trying to recall, but it will take time, so let's just look it up. Okay, so cesium atomic number. What? 55, yes. Yeah. Yeah, 55. Okay, so after knowing that, we can now proceed on having one proton, so that would be 55p, correct? Which is 55 times 1.6 times 10 raised to negative 19 coulombs. Okay. Next, we have two radios, so I'm going to just name them R sub E for empirical, then R sub W for van der Waals. Okay. Or V, sorry. Oh, let's just use. Okay, so for the first one, we have 265 picometers, which is equal to 265 times 10 raised to negative 12, correct, meters. And then we have 344, okay, which is equal to 344 times 10 raised to negative 12 meters. There you go. So for our required difference in electric field magnitude, correct, or electric field strength, so our equation would be, generally we're going to use E of E minus E of P, right? So knowing that the van der Waals radius is farther, so that means it must be weaker, its electric field, but how much weaker? So let's expand this equation. So this will be K Q source, right? So what's our Q here? So that's CS, right, divided by RE minus, to be squared of course, then we have K QCS over RV to be squared. Okay, so for our solution, you can just substitute now, right? So this will be what's K? 8.99, right? 8.99 times 10 raised to 9 Newton meter squared per coulomb squared. So I hope you have memorized this constant already. Okay, multiplied by 55 times 10 raised to 55 times 1.6 times 10 raised to negative 19 coulombs, okay, divided by, oh, let's use a ruler for this one. There. Oops. Okay, then we're going to use the ruler later, so we'll just set it aside there. Divide by, what's our R sub E? So this is 2.65. I mean 265 times 10 raised to negative 12 meters. Of course, that's to be squared. Okay, minus. So we place our minus here. So this will be the same for the numerator. So that's 8.99 times 10 raised to 9 Newton meter squared per coulomb squared. Okay, multiplied by 55 times 10, oops, times 1.6 times 10 raised to negative 19 coulombs, correct? Okay, Then we're going to use our ruler again. Somewhere here. Okay. Divided by, okay. Now we can hide this. Divided by 344 times 10 raised to negative 12 meters to be squared. There. So this will be equal to their difference. Okay. EDIF. Okay, so let's name this as our EDIF. So it will be defined like that. So after knowing that, you can now solve it on your own. So the difference between this is equal to, of course, you can now look for the answer. Alright, so after knowing this, we can now proceed on the third one, which of course I will be continuing on the next video. Alright, so for our next guided practice problem, so we're going to have a bit of an illustration here so you could understand it better. Okay, so by the way, if you're having a difficulty on understanding the problem, you may want to illustrate it. Like for this one, we're going to illustrate this so we would understand it better. Okay, so an electron which is initially at rest is placed in an electric field having a strength of 5 times 10 raised to 5 newtons per coulomb directed to the west. Okay, so that means we're going to place the electron on the west side of the electric field. So we're going to determine the acceleration, and then the acceleration of the electron, and then the speed it will be acquiring after moving a distance of 15 centimeters. Okay, so for our given, first we have an electric field which is 5 times 10 raised to 5 newtons per coulomb. Okay, and then we have charge of an electron. Okay, which is 1 point, so that's negative 1.6 times 10 raised to negative 19 coulombs, right? Okay, what else? We have distance. So in this case, I'm going to name our distance. Oh, let's just use R. Let's still use R. Okay, which is 50 centimeters. So that's 5 times 10 raised to negative 2 meters. For our required, we are tasked to look for acceleration first, then for velocity. Okay, for our equation, so this will be a very dependent on an illustration so you would understand it. Okay, so let's say we have our point charge, say this one, then we're going to place the electron on this side. Okay, let's say here something smaller, so let's have a charge here. Of course, the electron is attracted to the proton, so its motion will be moving here, but the electric field is moving on this direction, right? You got that? Okay, so first we're going to determine the acceleration of the attraction of the electron, of course knowing that it will be moving on this direction. Okay, because it will be attracted to the proton, right? Because that's what the rule of charges states. Anyway, you got that. Okay, so for this one, we're going to utilize the formula of electric force. So we're going to need force here. Okay, then I'm going to show you why you need to know the masses of the charges as well, because we haven't used that yet, right? So for this one, this is Q multiplied by the electric field, which is both given. In this case, these are given as, let's just change this as Q. So we don't have to redefine this one anymore. Okay. Then of course, knowing that force is also equal to mass times acceleration, so we could derive acceleration, which is one of the required. So we can write it like this. So in this case, you can now write electric force can also be stated as like this. So knowing that we're going to need acceleration, we can divide both sides by m, right? Cancel m on this side. So you're now left with our first equation, which is ue over m. So this is our first equation, right? So we're going to look for a. Okay, so for our first solution, so this will be, what's our q? Negative 1.6 times 10 raised to negative 19 coulombs multiplied by 5 times 10 raised to 5 newtons per coulomb, okay, divided by mass. So what's the mass of the electrons? Of course, you have to include that on your given. So mass of electron is, so you can now check your notes. Okay, so if you haven't memorized it yet, it's 9.11 times 10 raised to negative 31 kilograms. Okay, then for the protons, it's 1.67 times 10 raised to negative 28 or 27. We're just gonna check it if we're going to need it. Okay, but for now we have the electrons here, so there's that. So you just place it here, times 10 raised to negative 31 kilograms. Okay, C. If you're going to expand Newton here, okay, so let's expand Newton there. You can obtain the unit kilogram meter per second squared, right? Times coulombs, since we have coulombs here on the denominator originating from newtons per coulomb. So showing the cancellation, you can now cancel coulombs and you can now cancel kilograms, leaving you with meter per second squared, which is the unit you need for acceleration. See? Okay, so for the first answer, you solve for that one. Okay, so of course you already know the unit will be meter per second squared. Okay, as for the second equation, so what we need is velocity. So the distance is already provided, so you can now recall your kinematic equations. Okay, so since we don't have time, of course that's automatically the time independent equation, which is what? Final velocity, or v, is equal to initial velocity, so these are squared, right, plus 2a delta x, right? So since there's no stated initial velocity here and what we're looking for is final velocity, you just have to adapt the variables. So you have v squared equal to 2a. Instead of delta x, we're going to use r, since that's what we have used on our given, right? And now you can now proceed on your solution. So our S2 would be v, or you square it both sides. Okay, so cancel this one. Okay, so this will be 2 multiplied by the acceleration that you will be obtaining from the first portion of this problem multiplied by the radius, which is 5 times 10 raised to negative 2 meters. Okay, then since you're going to square root that, so you're going to notice that the unit for A is meter per second squared, so that's meter times meter is meter squared. Then you have second squared here, so your final unit for this one is meter squared per second squared, and since that's under the square root sign, so you're going to have meter per second as your final unit, so assuring that your final answer is correct. Okay, so V equal to something something at meter per second. Okay, by the way, returning to our first answer, what's stated on this one, so you were asked to the acceleration. So knowing that acceleration is a vector, let's state the direction of the electron due to the electric field. So what would be its direction? Since it's an attraction, if the electric field is due west, its attraction will be moving due east, right? You got that? Okay, so this is the part where we have to explain that we assume that point charges are stationary. Okay, so of course, realistically, supposedly they should be attracting each other with the force according to the Coulomb's law. But since we are trying to understand the concept of electric field in an elementary manner, we're just going to move one particle at a time. In this case, on this particular problem, the electron here. Okay, so we're going to assume that the motion of this particular point charge is stationary. Okay, so that means our electron is the one that will be moving towards our point charge. Okay, so the direction would be east since they will be attracting each other. All right, so that will be the same for the speed. Okay, but by the way, it's speed, so you don't need the direction actually, just for the acceleration. Okay, so that's it.